we're going to talk about thermodynamics. Our team is conformed by Jacier Ibanez, Rodrigo Orozco, and Andre Peniche. The first topic that we're going to talk about is the laws of thermodynamics. The set of law says that temperature is a property of any thermodynamic system, and thermal equilibrium will exist between any two systems if their temperature is the same. That means that if we have a body A that is in thermal equilibrium with a body C, um, actually we are going to have the same temperature between the two bodies. So it means that they have the same temperature, so they are in thermal equilibrium. A clear example of that is like when we get into cold or hot water, we will notice the difference between the temperature in our body and in the water. But after a few minutes, because of the set of the law, we are going to feel the water more comfortable. So we we say that there is a thermal equilibrium. Another examples of that is the thermometer. The if we take a glass of ice water and a glass of hot water, we if we place them together, after a few hours, they will eventually reach thermal equilibrium with the room. And another example, if you place a package of meat in your freezer, you assume that the meat has reached the same temperature as the freezer and the other items in the freezer. There, this is the zero law of thermodynamics. The first law establishes that the variation in the internal energy of a system is equal to the energy transferred to or by the surroundings in the form of heat and work. So that energy is neither created nor destroyed, only transformed. We can imagine this as the engine of an airplane. The fuel releases heat and does work that makes the plane move, which means that the energy was neither created nor destroyed. So the energy has changed from chemical energy to kinetic energy. The second law says that there is a limit to the amount of work which is possible to obtain from a hot system. This law can be understood to mean that the amount of entropy in the universe tends to increase with time. For example, if we burn a sheet of paper and then collect the ashes, we will find that it is less matter than it was. And the third law of thermodynamics says that the entropy of a pure and perfect crystalline solid can be taken as zero at the temperature of absolute zero. In an example, we can analyze what happens in a freezer. The food we put it will get so cold that it will slow down or stop the biochemical processes. Thus, slowing down its decomposition and making it fit for consumption for a longer period of time. So, in this law and in the previous law, we talk about entropy, but for a better understanding of the entropy and some and more concepts of thermodynamics, we are going to see them in latest slides. So, in first and second law conclusions, we have that these two conclusions are related with the universe because the first law says that the universe is a constant quantity and it expands a lot of time. And the second law has an important applications, and it's also useful for interpreting the origin of the universe, since it explains the energetic changes, and it has had and will have in the future?
I'm going to talk about the main concept in thermodynamics. The internal energy is defined as the energy associated with the random disordered motion of molecules. It is separate in scale from the macroscopic ordered energy associated with moving object. It refers to the invisible microscopic energy on the atomic and molecular scale. The enthalpy is a thermodynamic property of a system. It is the sum of the internal energy added to the product of the pressure and volume of the system. It reflects the capacity to the non-mechanical work and the capacity to release the heat. It is used to calculate the heat of reaction of the chemical process. Change the enthalpy is used to measure heat flow in calorimetry. Enthalpy is used to calculate minimum power of the compressor, and finally the enthalpy change occurs during a change in the state of matter. Where entropy, a measure of the unavailable energy in a closed thermodynamic system that is also usually considered to be a measure of the system disorder that is a property of the system state, and that varies directly with any reversible change in heat in the system and inversely with the temperature of the system. Work. Can you change, Rodrigo? Thank you. Work is an interaction between two systems, such that whatever happens in each system and its boundary could have happened exactly, while the only effect is external to that system would be a change in the level of the weight in a gravitational field. Heat. The heat is a form of energy, but energy is in transit. Heat is not a property of a system. However, the transfer of energy as heat occurs at the molecular level as the result of the temperature difference. The conventional symbol used to represent the amount of heat transferred in a thermodynamic process is Q. Uh, while internal energy refers to the total energy of all the molecules within the object, heat is the amount of energy flowing from one body to another spontaneously due to their temperature difference. Heat is a form of energy, but it is energy in transit. And finally, I'm going to talk about thermodynamic potential, are scalar quantities used to represent state functions. Together with the corresponding equation of state, thermodynamic potential describe the equilibrium behavior of a system as a function of so-called natural variables. And Rodrigo, can you change? Yeah, the last part. Chemical reaction. We have a chemical reaction, although we don't have the exact data, we can deduce its characteristics from the behavior of the elements in the equation. The I negative, the enthalpy, the entropy positive with a high temperature resulting in a spontaneous reaction. And that's it. Thank you and enjoy the video.
Listo. Ya.